Swayam Prabha. Digital India. Educated India.
All right, so like every bad movie, there is a sequel, okay? So I'm back. All right, so I have some slides which I thought I'll show you, but the most fun part of the slides are the animations which are not being animated on this. So I will have to show you on my laptop, okay? So with all those limitations, let's go ahead. So let's just recall what we were doing. We're talking about chaos, and by chaos I mean, so as I've put in this title more clearly, deterministic randomness. So that means that the rules are fixed. You don't go around changing rules because the rules are basically the laws of nature. And there is randomness, which appears like lawless land. So the connection between these two, deterministic randomness, that's what we're talking about. And we are just interested in simple things like Newton's second law is what I said. I've just written it down in a differential equation form. And as you guys know, this famous character, what's his name? Yeah, so calculus always carries this pendulum to do some weird stuff, but apparently that helps him find water or something like that. I don't know. No? Is that right? You guys have probably read Tintin.
To find buried treasure and all that.
Buried treasure, all kinds of stuff, right? Okay, so we don't know the signs of that, but we don't know that these are oscillations of some kind which are interesting. We discussed that last time, and here is a more mathematical treatment of the same thing. So this is the force equation. There is a single degree of freedom theta. The second derivative of that with respect to time is this restoring force, which is restoring it. So it's pushing it inside. That's the energy equation. Okay. And okay, but where are we? We are, of course, on this earth, which is also having these kind of forces. And Kepler's laws is what is dictating how we go around. Here is one of Kepler's laws, that the square of the time period of this motion around the sun is going as the cube of the distance, or semi-major axis. So this sort of a law is something which is very interesting, quite different from that of the pendulum time period formula. And this is coming from the same laws of nature in the sense that both of them are coming from gravitation. And so the question is, why are they simple? This pendulum, this Kepler's two-body problem, or the earth around the sun, why are they simple? And one of the things which I was discussing last time, emphasizing, was that the pendulum has only 1 degree of freedom. So it's rather restricted. It's got this angle which is changing with time, just one angle. And the Kepler problem, although it appears to be at least 3 degrees of freedom problem, if effectively becomes 1 degree of freedom because of a very high amount of symmetry, that is what I was talking about, that the force depends only on the distance between the two objects, which makes it highly symmetric. So you have conservation of angular momentum, high in energy, and in fact even one more law. So how can there be complicated dynamics in nature? And this is what we discussed sometime, discussing rather controversially why we cannot predict a simple coin toss, or can we predict at all? Weather also we mentioned. Of course, we would all like to predict when things like heart attacks happen. So these are increasing amount of complexity in this system. Coin toss, coin is a very simple rigid object. The weather is a much more complicated object in the sense that it involves the atmosphere, it involves flows, but that's also governed by the laws of physics. But it seems to be that we cannot predict the weather accurately. If you take biological phenomena, heartbeats are again a very regular phenomenon. You look at your ECG, you can see oscillations. The heart, your heart rate is more or less beating at a constant speed, but it's not like it's exactly periodic at all. And also the signals from our brain, the electrical signals, they are also kind of periodic but not quite. And especially heart, people have studied what kind of mechanisms underlie heartbeats, what kind of maybe differential equations. Are there differential equations which is governing how can you model heartbeats? And then what is a heart attack? So maybe there could be a sudden increase in the frequency of this. It's called a fibrillation. So suddenly the heart starts beating very fast. Can we predict these kind of events? So this is a very important, interesting set of problems. And then even more unpredictable in some sense, and where the laws of even physics don't seem to hold, are things like a stock market fluctuations. Except for some, politicians making decisions, and in that case, something major is going to happen. Typical day, you cannot say what's going to happen in the stock market. And a lot of people would like to, just as in gambling, one would like to see, because there's a lot of money involved. So stock market predictions. So there seems to be uncertainty and turbulence all around us. And this is basically what we were kind of trying to get at. What is the origin of this? What is the origin of chance itself? So coming back to this simple pendulum, we have to probably go beyond 1 degree of freedom, at least 2 degrees of freedom. Okay, so that's number one. Number two, the equations have to be nonlinear. So like this is a nonlinear equation because the force law is a nonlinear function of theta. So linear versus nonlinear, a function is linear, function is nonlinear. You can just take a nonlinear function as something which has higher order than just 1, like x is a linear function, x square is not, sine x is not, and so on. So we know that approximately sine theta is theta for small angles, and then this becomes linear. Not only is this function linear, because this derivative is also a linear function of theta, this entire differential equation is said to be a linear differential equation. And these linear differential equations have a very special property, which the nonlinear equations do not follow. Namely that if you give two solutions, a linear differential equation, the sum of these two solutions is another solution. So this is not true for nonlinear equations, nonlinear differential equations. So like when we think of waves, we may think of waves of some particular kind, and then adding on to another kind, maybe it leads to destruction and interference, constructive interference, and so on. But there are also solutions to the wave equation. So it's a linear equation. The harmonic oscillator approximation like this is a linear equation. That's why you can say that, well, one solution is cos omega t, another solution is sine omega t, and any general solution is just a sum of these two. We cannot say that for this. So these are important. So there's differential equations such as what I've written here, and there are also difference equations. See, differential refers to this time being continuous. Okay, the acceleration is written in this form. A difference, you think about it as time being discrete. So let's see. Oh, okay. I have more on the time simple pendulum, but this we discussed last time. The time period increases as the amplitude increases. The time period, in fact, approaches infinity as this amplitude approaches pi or 180 degrees. And there are two equilibrium points. One is stable, another unstable. The one is unstable at pi. At 0, it is stable. And there are two types of motions. One is oscillations, it just keeps going like what you saw in the calculus cartoon. And then rotations, when you have sufficient energy, energy is more than 2gl, it just rotates like this. All right, so let's look at some difference equations, okay, where time is discrete. So in fact, last time in our kind of free rolling discussion, I wrote down, I think, square root of 5 plus 1 by 2, and you guys said it's golden mean. So what is this equation? It's a difference equation for something called f subscript n. N is now integer, 0, 1, 2, etc., maybe even minus 1, okay? And this tells you that if you have the n minus 1th number fn minus 1, n minus 2th number fn minus 2, you add them together to get fn. So this is an equation of a difference equation, and it is second order difference equation because you need two numbers to decide the third number, okay? So this is a second order, like that differential equation of the pendulum or Newton's laws is second order in time, you need a second order. So with some initial conditions, so let's take this f0 to be 1 and f1 to be 1. What is the sequence that you get? A Fibonacci. By the way, I believe it's called the Pingala Fibonacci sequence. It's known to Indian mathematicians long before that. According to Wikipedia's Pingala, I'm not an expert on this. There was also a person called Narayana who has another very interesting set of contributions, including a third order difference equations. Huh? Difference equation. What is that? Yeah, there will be like fn minus 1, fn minus 3. So then there will be third order. Okay. So anyway, so this is a sequence which you know very well. 1, 1, 2, 3, 5, 8, etc. And the ratio of any of these two numbers, say consecutive numbers, tends towards the golden mean. And here are some facts, right? You know an exact formula, you can derive an exact formula for f subscript n in terms of some 1 plus square root of 5 by 2, 1 minus square root of 5 by 2 to the power of n. If you haven't done it, you should try to solve this for fn and write the nth term without going through this recursive process. Now, we are not really interested in that, but I'm interested in pointing out that this is increasing at an alarming rate. It's increasing what's called exponentially. This fn is going as e to the gamma n, where gamma is in fact the log of the golden mean. So because this fn itself is going as golden mean to the power of n for large n. That's what this tilde means, not an equal to. Is that clear? I mean that this thing is growing, and it's in fact growing pretty fast at a rate which is given by this. Now still there's no chaos or anything like that, it's just growing very fast. Now suppose somebody gave you this sequence, it starts to look like the Fibonacci 1, 1, 2, 3, 5, 8, 13, but instead of 21 we have 7. And then instead of 34, 6, 13, 5. So can you tell me what the sequence is? And can you then predict what is the next number? Does this follow any law?
Yes.
What is it?
Sir, the consecutive numbers and subtracted give the
Huh?
it works as like in pairs.
6 plus 7.
So there are triads of numbers where the sum of first and second
Get
is
it
equal.
backwards.
So there are triads of numbers where the sum of the first and second gives with the
First and second triads of numbers like 5, 4, 9. Yeah,
but
5, 4, 9. 9 is 5 plus 4. Yes.
at certain points
7 and 8 it's 9. 9 and 8 it's 13. But here is not 15. So good point. So it's very closely connected obviously to the Fibonacci. But you see the Fibonacci is increasing very exponentially. But what is the largest number you see here? So that should give you a clue also. Nothing is there more than 13 in this.
Okay, now once you reach 13,
Yes.
once you reach 13, you subtract the subtract the number two times before it. Okay. 13 minus 5 is 7. 13 minus 7 is 5. Okay, my bad. Mathematically,
Huh? I mean, the rule is simple enough.
One from the previous number of the people.
Once we reach 13, the
Before
previous
13
number
is
is
8.
subtraction.
The next one is 21. So what do we have to subtract?
Once we reach 13,
Ah, yeah, 7.
yeah, 13 comes from 0 minus 1.
The next number is 1 less than its previous number. After 30. So,
Ah,
after 13, the next number is 1 less than its preceding number. After the number preceding 30.
1 less than?
Its preceding number. So, like after 13, that's 7, which is 1 less than 8.
Yeah, but is that law holding throughout? You see the next is 6.
Yes, sir.
So what is that?
Yeah.
Or then 13. 13.
Yes, sir. 5
Next is
like
5.
less than 6.
Huh?
Same thing.
Yeah.
Exactly. Before the
For example, if you take 9 and 13 together, you add 9 and 13 to get 22. And you take the difference of 22 and 14.
Sorry, where did you get 9?
Like,
Calculate 6 by 4.
so you have 1, 2, 3, 5, 8.
Yeah.
8 plus 13 is 21.
Right.
Subtract it to 14 and you get 7. And 7 plus 6 is 13. Let it just be like that. And 6 plus 13 is 19. 19 minus 14 is again 5. And 5 plus 4 is 9. And 4 plus 9 is 13. But 9 plus 13 is again 22. So you subtract 22 minus 14, again get 8. And you just get the same thing like that. 8 plus 7 is 4.
Okay, very good. I think you have cracked it. Very good. So, what has been discovered is a law. There is a law, although this looks random. 13, 0, 13, 13. Somebody gives you this bunch of numbers, you may not immediately recognize it as coming from Fibonacci. So what actually is there, let me write it very simply, is that this law is called Fn modulo 14. Okay, the nth term is modulo 14, which means that a modulo means is basically the remainder when you divide by that number. Here that number is 14. Okay, is a remainder when you have something which is less than 14. So this is always a number which is any number from 0 to 13, because these are all the possible reminders when you divide by 14. Okay, so now you can go anywhere, you don't need to rely on anything. 6, 7, 6, 4. If you take modulo 14 of that, that is you divide by 14 and find its remainder, you will find one of these numbers which corresponds to that. Okay, and So that's why you're finding that some of them is looking like 5 plus 4 is 9 because it has not gone above 14. So modulo that. So the rule is still fn minus 1 plus fn minus 2 modulo 14, and all these things are integers. So this law holds. You see, in this mathematical simple model is actually a lot of important physics. The physics is coming from two things. One is here, this is growing exponentially, and this is growing exponentially is a model for instability. Okay, things are unstable, they are flowing away. In time is just growing, but it's not like it's unstable, but it's not going away to infinity because of some finiteness in energy, or things can't go beyond a certain boundary. It's remaining there in some finite space, and that is this modulo operation. The modulo is folding the trajectories. The exponential is pushing the trajectories apart. Actually here there is no trajectory, it's just a number. But as a model of that, this is a very accurate thing. But actually it's an amazing fact that, what do you think? Do you think this will repeat after some time, or what do you think? If we keep doing this, will this keep giving you some very random looking sequence like this, or will it start repeating? I mean, yeah, 6, 7, but is the whole thing repeating? I don't see any repetition here. The whole thing, by repeating I mean like 1, 1, 2, 3, 5, 8, 1, 1, 2, 3, 5, 8, etc. We don't see that yet, but I encourage you to write a simple program and to actually find out if this is repeating. Okay? I won't tell you the answer. Yeah.
Analytical method of showing it will repeat or not repeat, or is it only computation?
No. Once you know that it repeats, it's a complicated problem actually. Once you know that it repeats, then you can try to find the period. It's not so easy a problem. It involves, so I'm not sure that I have a picture of that, but those of you who want to look at this more carefully, there's a very closely related system called the Arnold Cat Map. These things are also called maps. These kind of difference equations, are also called maps. In fact, let us try to write this. Let me try to. Let me call this fn minus 1. Okay, so we have fn to be fn minus 1 plus fn minus 2, let me call that gn minus 1. Okay, so gn minus 1, what is that? Gn minus 1 is fn minus 2. So what is gn? Fn minus 1. So I can look at the one second order difference equation of that kind as a set of two first order difference equation. This is a trick that mathematicians play, and not only mathematicians, physicists, very important differences in physics when you go from second order to first order. But you see, this is completely equivalent to that, with the understanding that you give the values of f1 and g1. Okay? But now you see what is the, let us see, let me see how much I can push your boundary. Do you guys know matrices? You studied in school?
Yes.
Really? Huh? Mangal Sundar, okay, not in school, right? You have some algebra, linear algebra, yeah. Okay, so you can write this as a matrix. So let me try to write this as a matrix. Fn is a vector, 2 entries. Okay, so I'm going to write here a 2 by 2 matrix. You will help me identify it now because Mangal Sundar has told you. Fn minus 1, Gn minus 1. Tell me what are the elements here? 2 by 2 matrix. Huh? This one here. Huh?
You have to find the matrix.
A, B, C, D. Find out A, B, C, and D. It's a 2 by 2 matrix. Huh? 1, 1, 1, 0. That is matrix multiplied by a vector. Okay, row, column, row, column. All right. So this Fibonacci sequence, we can look at it as a matrix multiplication of this kind, with this matrix being 1, 1, 1, 0. Agree? Very good. Now we have recipe for disaster. Now let's then look. Let's look at F1 G1. Okay, multiplied by 1, 1, 1, 0 is going to give you F2 G2, right? All right. Now what is F2 G2? I want to get F3 G3, right? That's going to be this 1, 1, 1, 0 multiplied by 1, 1, 1, 0, right? Because 1, 1, 1, 0, sorry, F1 G1. Okay, F1 G1 is equal to F2 G. All right. Now tell me, what is this matrix? This matrix 1, 1, 1, 0 multiplied by 1, 1, 1, 0 itself, square. So this has to be a matrix A, B, C, D times F1 G1.
So it will be 2, 1, 1, 0, 2, 1, 1, 1.
2, 1, 1, 1. 2, 1. Okay. So again, row, column, 1 into 1 plus 1 into 1, row into column, row into column, row into column. Okay. So you see now this, if we take this as the, by the way, I can also do this right here. I can say that I can, we can now go ahead and find out what is Fngn, okay, in terms of these numbers in here. You can find out what these things are. In fact, the entries to this matrix will be from the Fibonacci sequence. But, yeah, I mean, it will be just some, you can see what that is going to be. So, but what I want to say is actually, suppose we forget about this Fibonacci and take this, suppose we give you some x and y and we multiply by 2, 1, 1, 1, it gives you, let me take xn, yn, xn plus 1, yn plus 1. Okay, so this is a recipe which I am getting from that Fibonacci sequence thing, except that here I am not going to put integers, I am going to take any number between 0 and 1, real numbers, okay, and I am going to
Shouldn't it give xn plus 2 and yn plus 2?
no. So I'm just motivating that from the Fibonacci.
Okay, but only in those series.
I'm not writing even a series. I'm saying that from this kind of a thing, I'm going to another system. So if you want, you can think about it as, but here I'm constrained by taking integers and so on. I'm saying that let us now define a new system like this. It's properly defined. Given an x0 or y0, you know how to find x1 and y1, okay? And so on. So now you can now take powers of this matrix, but this is not so much fun. This is actually as much fun as a Fibonacci sequence itself, in the sense that this xn and yn will be growing exponentially. they'll be increasing very fast. Okay, the fun comes when you do this modulo 14 kind of an operation on this, and you keep it within the 0, 1. How will you keep a thing within 0, 1? Modulo 1. Okay, that means that modulo 1. Modulo 1 means that you take the
Sir, modulo 1 will have no reminder.
modulo 1 means you take the fractional part of it. Okay, you have the integer part and the fractional part. You take only the fractional part. Huh? In this you're saying it can be. It will become 0. So 1 and 0 are identified. Okay, it's like a circle. It's like a circle. 1 and 0 are identified. So let's look at this modulo 1 operation a little bit more, because we might use it later on. 1.2 modulo 1. How much is that? Okay, very good. Minus 1.2 modulo 1. 0.8. Okay. The fractional part, but it's positive. It has to lie between 0 and 1. So you can take an integer, you can add. So basically you have to add or subtract an integer so that the result lies between 0 and 1. That result is the modulo 1 result. Basically it's like wrapping this on a circle of radius 1 or circumference 1. Alright, now this is a well-known chaotic system. Just as this thing is proving it to be very random, this is also a very random system. This was studied by this mathematician, physicist called Arnold, and it's called an Arnold Cat Map. It's called an Arnold Cat Map because Arnold put a cat on this. So let me see actually if I can show you a picture. Not bad. All right. So Arnold put a cat on this and he saw what's happening to the cat. So you see, now it's a modulo 1 on both x and y. So what kind of an object is it? So 0 to 1 along the x-axis, 0 to 1 on the y-axis is a square. Okay? But modulo 1 means you're identifying 0 and 1. You're also identifying the 0 and 1 on the y. What sort of an object is this?
Normalized.
Huh?
Normalized.
Not normalized. What kind of a geometric object? See, if you identify these two,
Cylinder.
this is a cylinder. Now you take a cylinder and you identify a line. You're taking a cylinder, fold the cylinder so that the caps are together. Ring, exactly. Otherwise known as meduvada, right? Yeah, so it's the topology is that of a meduvada. Okay, otherwise in scientific parlance known as a torus. A torus is two circles put together. Okay, now what you do is you put a cat in here and you see what happens to this cat's image as this map happens. Now what is happening? There are two things in this map. One is the stretching, which is coming because of that Fibonacci kind of sequence. It's exponentially stretching. The other is folding, which is coming because of the modulo. So the cat is being stretched and folded, and the poor cat is not left alone. But since I don't like violence to animals,
So can we say that it's also a cat map because it's a highly unstable state that's represented?
no, it's called a cat map because Arnold put a cat in it. You can't change that fact. Okay, so, all right. Can you guys see what is there in this? Now, you're too young for knowing this president of the US, but he was a president called George W. Bush. So when I made this animation, I believe he was the president. Today I might have put some other person there. And he was carrying out a war in Afghanistan, Iraq actually. Iraq, yeah. So, but this is what happens. He was on this cover of this. Anyway, this is taken from some other site. But the point is that there is his image, this image on this unit square. This is what happens after one iteration of the cat map. One iteration, you're seeing this thing being pulled and then it's being folded. But you can still see some features in this. Okay? And then this is after 2 iterations. You can see that this being pulled more than 3, 4, 5. In 5 iterations, this image, every aspect of that image is here. Nothing is destroyed. Nothing is destroyed in the sense that I can now go back. This is a reversible operation and get into this. But this is what chaos is doing. It's scrambling up things in a deterministic way. Okay? So this action is essentially the effects of chaos, and it leads to all this kind of equilibration and so on. And there are 2 ingredients, as I mentioned. One is the stretching and the other is folding. And that's the aspect of this cat maps. But you're seeing this very simply in this digit sequence. That's why I wanted to put it in there. Now, why I mentioned this, because there was a question also about whether you can predict the period. People, when they first found this, Arnold didn't himself realize this, but when people put it on a computer like this, they realized that after a very long time, the cat was coming back. The original image was coming back. That meant that there is something very special about these powers of these matrices modulo some integer, not 1. Modulo 1, if you take integers and take modulo 1, you will get 0. Modulo some integer, and do you know, can you imagine why that is so? It's because when you do a computer calculation, a computer image is always a finite matrix. Okay, you have some 256 by 256 image, 1024 by 1024 image, pixel values. Your eye thinks as if it's an image, but obviously there's no continuum. It's all discrete. Okay, so what happens is, actually when they were doing this on a computer, you have a grid. And that grid was being taken from one point to another point and so on. And it turns out that for the cat map, because of this integers here, any n by n grid will get permuted into itself. It will just be shuffled into itself. And therefore, if you can find that this is equal to identity, then that will be the time period at which this cat map will recur miraculously. The cat never dies. So, to find this time period is a hard problem. There's a famous mathematician called Dyson. Physicist and mathematician. So he tried to find the period. You can Google it up. Okay, so now let me go ahead. By the way, again, like last time, I think I'm at the border of my talk. What's happening at 3 o'clock? You're supposed to be going to see your project advisors?
Yes.
Very good. Your project advisor is expecting you, right? So then let me stop with this. Let me show you some animations because I didn't get around to that, but now it's not working on this. Okay, so double pendulum we saw last time itself. Okay, as physical systems, we saw an actual double pendulum. This is just a simulation of that. And the important thing is that there's more than 1 degree of freedom. There's here 2 degree of freedom. In fact, things will get even more interesting if you have more degrees of freedom. This is a triple pendulum. Okay, there are 3, like, I can't do all that, huh? So, hold on. Oops. Okay. Yeah, sorry, yeah, go ahead.
So I have a question, sir. In
Yeah.
double pendulum, energy is conserved and angular momentum is conserved. So
Double pendulum, energy is conserved, angular momentum is not conserved. There is torque because of the action of the gravitational field. Okay, so actually what you're seeing here as this mess in this triple pendulum, let me try to play that again, is that there are, what you're seeing as one pendulum is not one pendulum. There are actually several triple pendulums, 40 I think, and that's why you're seeing after some time all of them are totally different from each other. For that, and you know what that time is called? Last time we discussed the Lyapunov time. So now they're all together, the 40 of them. Suddenly they decide that, look, the Lyapunov time has come and they're all diverging from each other, and it looks like they are completely different. So this is the sensitive dependence on initial conditions that one is talking about, and which will not be there. Now a similar thing, I mentioned billiards last time. This is the stadium billiard. So it's a bunch of particles starting together, right? And then you can start seeing how they are diverging with successive intersections. I thought it will go for longer. Yeah, maybe this one goes longer. Yeah, so now that's what's happening here. Also there is this Lyapunov. By the way, that particular simulations I got from this website called Dynamical Billiards. Julia is a programming language which is built like MATLAB and Python, but especially meant towards physics and linear algebra. So this is a Julia website, dynamicalbilliards.julia. All right, so I have more on this logistic map, but I think we started discussing a bit of that last time, but I think I will allow you to go and do your project. But let me just show you the simplest, or maybe because this doesn't involve an animation. Yeah?
could you do the rest of the logistical map sometime later?
Difficult, because I think you guys are, not much is there. Actually, there is a very simple point in the logistic map when r is equal to 4, when there is full chaos. So by the way, that's the logistic map. So that's just a first order difference equation. Given xn, you find xn plus 1, but it's non-linear. And it shows chaos as this value of r is changed. So r equals 4 is one where there's full chaos. Here you see sensitive dependence on initial conditions. I've just plotted xn versus, this is time, this is xn. And there are two things, red and blue. And you can see that they are together for about 20 time steps. Afterwards, they are far apart. That's exactly what happened to the other.
So what's the difference in initial conditions?
It's some 10 power minus 6 or something like that, so that you can't see that. You can vary that. I would have taken something like 10 power minus 6. Okay, so I think that gives you some idea of the dynamics of chaos. Anything more is details. Okay, so please go ahead and do your projects and have fun. And I'm there anyway for you to talk when you want. Okay? All right. Goodbye, guys. Thank you very much.
gratitude to Professor Arul for an enlightening lecture on the origins of deterministic randomness. We appreciate the time and effort Professor Arul dedicated to sharing his expertise with us. Thank you, sir, for inspiring us with this astounding lecture.
Swayam Prabha. Digital India. Educated India.